we have to have a way to count atoms. All right. People in the old days would take a piece of magnesium, burn it in air, and they would create magnesium oxide. Magnesium oxide is kind of like a white powdery kind of stuff, this stuff here at the bottom. And the magnesium itself is a very fine kind of metal. And people studied the ash relative to the metal, and they saw that the ash had more mass. And these pictures right here, the left-hand side is magnesium, and the right-hand side is a magnesium oxide. It's MgO. We'll see later how that's happening. But if you don't know how much oxygen to add to the magnesium or magnesium to add to the oxygen, you're going to get yourself in trouble. So chemists need what's like a counting unit so that we can add like one correct amount of oxygen to react with our amount of magnesium. And it's a really cool kind of tool that people have developed. So in science, the counting unit that chemistry uses all the time is called the mole. Woohoo, the mole is so cool. Anyway, the mole is not the little dude that runs around in your grass if you have it and like makes holes and stuff. Those are sometimes gophers, by the way, too. But anyway, the mole in chemistry is similar to the idea of a dozen. And if I said to any of you, hey, go get me a dozen donuts, you'd probably have no problem going to the store and getting me 12 donuts because a dozen is 12 and 12 is a dozen. But you could also get a dozen roses or a dozen cans of Coke or a dozen coffees, whatever kind of thing works it out. You don't have to actually think about it as 12, but it's a counting unit. And of course, 2 dozen would be 24, twice 12. Half a dozen would be 6, etc., etc. The mole is really similar to the dozen. Mole was first named by this guy Ostwald in 1893. It had been proposed by a guy named Avogadro, but Ostwald was the one that thought of the name the mole, which is kind of cool. Speaking of Avogadro, Avogadro was apparently a very shy mathematician, and you can see the dates there a long time ago. But anyway, he was the one that first proposed the idea for a number. And now we call this number Avogadro's number. Sometimes it gets the symbol N, big N sub A, but that's one anyway. Avogadro's number is a really important number in chemistry, and this is the full version, 6.022140766. It goes on for a longer, times 10 to the 23rd. I really want you to know / memorize 6.022 times 10 to the 23rd. We're going to use that number a lot. And if you have to keep looking it up all the time, that's going to be a real drag on your time and kind of annoying. So if you know 6.022 times 10 to the 23rd, that's awesome. And this number refers to the number of units in a mole. So if you're talking about copper, an element, that would be number of atoms of copper in a mole of copper. If you're talking about a compound, for example, CO2, the smallest piece of a compound is a molecule. So a mole of CO2 would be 6.022 times 10 to the 23rd molecules of CO2. So again, that 6.022 times 10 to the 23rd, kind of a weird number, but it is like a dozen, like 12. All right, and 12 is a dozen and a dozen is 12. Well, 6.022 times 10 to the 23rd is a mole, and a mole is 6.022 times 10 to the 23rd. If you have exactly 12.00 grams of pure carbon-12. And pure carbon-12, by the way, is hard to get because there's other isotopes with most carbon. But if you have exactly 12 grams of pure carbon-12, then you're going to have exactly 6.022 times 10 to the 23rd atoms of carbon. And they call this 12-gram number the molar mass. It's 12 grams of carbon in 1 mole of carbon. And this is only for pure carbon-12, by the way. Now, all of the isotopes of carbon makes the mass a little higher. If you look on the periodic table, the mass is going to be a little bit bigger number. Mine is 12.01. Here I use 12.011, and you can get into better values. That's just because carbon isn't pure carbon-12. There's also carbon-13, a little carbon-14. But all of those numbers on there, on the periodic table, those are are molar mass numbers. They're also called atomic mass numbers. We'll talk about that in a little bit. But the main use that we're going to use in Chem 221 through Chem 223, molar mass. It's the grams of that element in a mole. And we'll talk about this. If you have pure carbon 12, that's 12.00 grams of that, 6.022 times 10 to the 23rd. And all the isotopes together would be 12.011. So all of these molar masses, or as they're also known, atomic weight, and either way is fine, they're all listed on the periodic table. So aluminum on this periodic table here, 26.9815. My aluminum is 26.98. That's okay. You can get, of course, better and worse ones, but it's the other really important thing on the periodic table. So again, all good periodic tables should have the atomic number, that whole number. They'll have the symbol for the element. So 13 protons is aluminum with the symbol Al, but it's also going to have this number, which is called atomic weight or molar mass. And we're going to see they're the same number with two different uses. Here's a type of a problem you might see. It says, what's the molar mass of an element with an atomic number of 12? So I'm making you think about what these different things mean. An atomic number, if you remember from earlier, that's not the molar mass number, that's the number of protons. So if you look on your periodic table, atomic number 12 is magnesium, Mg, and it's the other number on your periodic table, which is what you want for this answer. Now, for my periodic table here, Mg is 24.31. If you had a better periodic table with more sig figs, it'll be a number better than that. But you can see that the answer here, which is closest to 24.31, is D, 24.3050. So atomic number means number of protons. That's magnesium on the periodic table. And that 24.3050 is the other number that's listed on the periodic table. These are all 1 mole amounts, all right? Sulfur, magnesium, tin, and silicon. So the copper that the person is holding, copper, if you look on the periodic table, about 63.546. So that person is holding 63.546 grams of copper. The sulfur on the far left, sulfur is about 32.07 on my cheesy periodic table. Yours is probably better. So that's about 32.07 grams of sulfur. And there's magnesium, 24.3-ish grams, tin, etc., etc. The densities of the elements are different. So that's why sulfur looks like it takes up the most volume, but all of them have different densities. Copper is a pretty relatively high density, so it takes up less volume. Oh, it's all coming together. So here's a problem you might see. What amount of magnesium is represented by 0.200 grams, and how many atoms is it? Now, if you have a small piece of magnesium that has a mass of 0.200 grams, it would literally fit on the pinky of your hand. All right, it's a very, very small amount. It doesn't look very impressive. But let's figure out the amount of moles, all right, using the molar mass. And with a good periodic table, magnesium, 24.3050 grams. So I'm only going to use 24.31 here. And this brings up a good point. Chemists are always obsessed with sig figs. This is a 3 sig fig number, and you never want the molar mass to limit your sig figs. So if I use just 24 here, that would be bad form. You could use 24.3050, but it takes more time to enter in your calculator or make the little graphic like I did. So you always want to have at least 3 sig figs going forward. I used 4 sig figs here, so I cut 24.3050 down to 24.31. Most of the time, using a molar mass to the 100th, which is 2 decimals to the right, places to the right, is enough sig figs, but that's just a rough guide. Regardless, you can see here that those numbers on the periodic table are grams per mole, starting with the grams, 0.200 grams. Grams on the bottom and grams on the top cancel. In your calculator, 0.200 divided by 24.31, you get a number. It's going to be like that. Round it to 3 sig figs, 8.23 times 10 to the minus 3 moles. And again, we're rounding it to 3 because the top number is 3 sig figs. I used a 4 sig fig, 24.31. The final answer has to have the smallest number of sig figs, 3. And again, you could have used 24.3050. That would have been fine. It just takes more time, but either way is okay. Now, 8.23 times 10 to the minus 3 is not a very impressive number. I don't know what that means. That doesn't mean anything. It's a smallish number, but I don't know. But the next part is kind of cool. How many atoms are in this piece of magnesium? Now remember, a dozen of anything is 12, and a mole of anything, 6.022 times 10 to the 23rd. So we're going to take that mole number and multiply it by Avogadro's number. We're going to turn moles of magnesium into atoms of magnesium using Avogadro's. So if you take that mole and you multiply it by 6.022 times 10 to the 23rd, the moles on the top cancel moles on the bottom, still limited to 3 sig figs because our Avogadro's number had 4 sig figs, and you get the incredibly large 4.96 times 10 to the 21st atoms of magnesium. And I want you to step back for a second and think about that number. 10 to the 3rd is 1,000. 10 to the 6th is 1,000,000. 10 to the 9th is 1 billion. You have more than 1 billion, 10 to the 18th atoms in that little tiny bit of magnesium that fits on your pinky. All right? These atoms are so small, they hardly take up any space at all. And just a small amount, in this case of magnesium, has just an enormous number of atoms. It's just crazy. So think about these numbers as you go through. They're astronomical, how big some of them are. And as you eat a piece of cake, or if you drink some of my beloved coffee, all right, you're consuming just an inordinate amount of atoms at any one time. And that's what happens in our day-to-day life. It's just amazing. But anyway, Avogadro's number, the key to figuring it out. Notice we went grams to moles to atoms. You always want to go through that step. You could also go atoms to moles to grams. You could go the reverse step, but you wouldn't go grams to atoms directly. You have to go through the moles. Let's say that I have 3.011 times 10 to the 23rd atoms of pure carbon-12, and the question is, how many grams of carbon-12 do I have? Okay, so I'm starting with atoms this time, and I want to get to grams, so I'm going to go atoms to moles to grams, the opposite, like we just talked about. To go atoms to moles, I'm going to use Avogadro's number, and from moles to grams, I'm going to use carbon's number. And since it's pure carbon-12, that means it's exactly 12 grams per mole. So mathematically, you could take the number of atoms we're given with, divided by Avogadro's, 6.022 times 10 to the 23rd. But notice if you divide by that number, the 10 to the 23rds cancel out. 3.011 divided by 6.022 is half, all right, 0.5000. That's the moles. And then half of a mole times 12 grams per mole is how you can find the answer. Now, if that was too weird, here's the worked out answers. First part, here's the number we were given. We're dividing by Avogadro's number to get the moles, and it's exactly half, 0.5000 with lots of sig figs. Then you go moles to grams using the molar mass. Pure carbon-12 is exactly 12 grams per mole, so that means we have 6.000 grams of carbon-12, or answer C.